Welcome to the HSPF training by DSI. This is Anurag Mishra. In this video, we'll look at the different hydrologic parameters of a pervious land operation in an HSPF model. So a pervious land has far more hydrologic parameters, and we'll look at some of the key parameters only. So in this operation sequence, I added one more operation called PERLND 1. If you notice, the reach res is after the PERLND operation and after the implant operation. It's because later on I want to connect these operations, and the water calculated from the operations implant and PERLND will go to reach res 1. So HSPF wants to ensure that the processes in implant and PERLND have been calculated before it does the calculation for the reach res block, reach res operation. So that is why the sequence matters. If you put reach res before implant 1 and run the model, but in later on if you connect implant to reach res 1, then HSPF will give you errors. Okay, so we use the similar UCI file as before, as implant, reach res, PERLND. So reach res ended, now PERLND operation started. Now, again, activity, print info, binary info, and general information is same as before. Here the name of the operation is mixed forest. So let's look at pivot POM1. Again, these are the flags, and these three parameters are about the algorithm that will be used, and these are the flags that tell these parameters will vary monthly or not. And then there is high water table, irrigation, more than one number of canopies, those kind of a little bit more complicated models. We'll probably explore them in the later chapters, later courses. Pivot POM2, and then it has 3, 4, 5, 6, 7 parameters, and it has the hydrologic parameters are in 3 tables: POM2, POM3, POM4, and depending upon some of these flags, we can have P-water POM5 and POM6 also. In general, this is for when we are doing snow simulation around the fraction of area that can transpire in the winter. This is the storage, infiltration rate, length of overland flow, slope. K-vary controls the groundwater flow, and again the groundwater flow rate. PET max, PET min we talked about earlier. These are the coefficients of the equation. Generally kept default. This is the amount of water from the active groundwater that we can lose permanently. This is the evapotranspiration that is happening from the riparian vegetation. This is the evaporation that is happening from the groundwater that is very close to the surface. This is the amount of water that is stored in the interception storage, upper zone storage, Manning's roughness coefficient, interflow recession coefficient, and lower zone evapotranspiration. Now, some of these parameters, CEPSC, interception, since I provided the value for VCS as 1, that means this value is ignored, and rather a MON-intercept table is expected, and the values should vary monthly. So we have to provide the monthly value of interception at the start of each month. UZSN, all of these parameters can vary monthly, but we have to set up in the flag. Similar to IWAT state 1, we have PWAT state 1, initial storage of all of these storages. Again, when you have snow, then you will have more of these kind of initial storages. When you start a model simulation in January and your storages are not proper, it can skew your calibration for quite a bit of time. So It's important to look at the initial initial parameters. And if your first year is very wet and then you have not provided these values correctly, it can really affect the results later on. Okay, next, these things we have already looked at. PERLND, again, two lines added where the precipitation and potential evapotranspiration is provided as a time series, similar to the way they were provided into implant. Now, here we have, what I did was that I added a line called PERLND 1, and 100 acres of PERLND 1 are going to reach this one. But the mass-link table is different. Mass-link table is number 2. Let's look at number 2. So number 2 is similar to number 1, but the names of the volume and group are different because in the pervious land, that module is P water, not I water. And the sum of surface runoff, interflow, and groundwater is called PERO. If I write SERO, that means only surface runoff will enter here, not the interflow and groundwater. So that's why it's different here. Again, it's going to the same place. So that's it. So it is similar to the impervious land. And now I added one more line that tells the network. So if you want to connect this reach to another reach, so for example, this reach is, let's say there was another operation called reach test 2. If this reach was flowing to another reach 2, for that we'll provide a different table, and that table where is provided that reach rest row flow is the volume of water that is going out of reach, that is calculated at every time step, that is added to the inflow of reach. And since it's just the volume of water going from one reach to another, it does not need an area factor. When it's blank, that means it's 1. So that's how the different operations in a watershed are connected. In more complicated watersheds, you can have water flowing from one impervious land to one pervious land, or one pervious land to another impervious land. Those will require a lot of GIS work beforehand, and so that's possible. So all of these different connections are actually possible. It depends on the pre-processing that you can do and you can achieve. So this sets up our basic structure of a UCI file, basic structure of a time series file, and how different operations in a UCI file are connected with each other and how they make a watershed structure. So now that we have all this information, we'll move to the HSPF300 course, and in HSPF300 course, we'll actually make a UCI file from scratch. And since we understand all the parts of that UCI file, we'll be able to go through it and do more operations with it and make some more complicated UCI file. If you have any questions about any of those parts, how these schematic connections work, feel free to ask me questions. You can ask those questions in the YouTube comment block, or in our GitHub repository, or in the Basins group on the LinkedIn website. So all of these options are available to you. That's it from me. Thank you.